So good morning, my dear students. Uh, One instruction from another department is once you just log in, so please type your USN in the chat box. So I want everybody to type your USN in the chat box because once you just the participant list, we are getting only sometimes we don't display the name and the USN. So better type your USN in the chat box, and that will be taken as an attention. Okay. Yeah, so today we will going to continue with the things what we left out in the last week. So in the last week, we were just started with the characterization techniques for metal powders. I just give an introduction to the characterization techniques with respect to the chemical composition and the structure. Okay, so today we will just for a few minutes we will just review the things, and the later part I will go to take we will going to continue with the characterization technique. So in the last class, we were talking about the chemical composition and structure of the powder, right? So there, the level of impurity elements in the metal powders can be very significant to both the processing and properties of the final. So in the sense, during the manufacturing or during the processing of metal powders by different techniques, so there may be a possibility that the impurities may be present in the metal powders. So these impurity elements definitely will have its significance over both the processing and the properties, and the processing and the properties of the final product what we do. So therefore, it is very much necessary for to know what are the impurities present in the metal powders, which whether it is in the form of an elemental form or when it present in the chemical form. So it is very difficult for us to know. It is very important for us to know. So what kind of impurities that will be present in these metal powders? Okay. And also, these impurity elements on the hardness of the particle and degree of chemical reactivity will affect during this sintering will differ widely. So depending upon the actual form they are in. So whether they are existing in the elemental form or in the chemical form or chemical compound form. So the effect on the hardness as well as the degree of chemical reactivity during sintering will going to be differs. Okay, the annealing of the powder in the reducing atmosphere is an effective way of reducing the oxygen content. Since we are discussing in the last class, I will go a little bit faster here. Yeah, and then the microstructure of crystalline powder has significant influence on the behavior of the powder during compaction and sintering. And since what kind of microstructure the powders are having, and this microstructure will also have an influence over the powder behavior of the powder during compaction and sintering. And fine grain size is always desirable for us. And the grain size can be dependent on the powder particle size. A particular powder production method, what kind of the rapidly cooled powder will generally naturally give rise to small particles and also small grains. These are the one things what we said. And also, I think I just ended the last class with this concept of particle size and shape. Quickly, I will just refresh this. The shape of the powder is characterized by dimensionality of the particle and its contour surface. Most powder particles are three-dimensional in nature, and they can be considered as being somewhat equiaxed. So all the powders are multi-dimensional, means three-dimensional, and they are equiaxed. And most preferred shape of the powder is a spherical shape. Okay, and the porous particle differ from irregular ones because of the presence of porosity, which itself may be very irregular in both shape and size. Okay, so these things I'm just talking about, and the different distribution of the powders, so which we can have accurately what we generally say the size of or the size or the shape of the powder. So that will be depending upon the size distribution, which accurately describes the powders, right? So therefore, there are 3 or 4 different distributions we were discussing in the last class. One is the unimodal distribution. So there is a one high point and a maximum amount of certain critical size. I think this we discussed in the last class also. So there will be a Gaussian distribution like this. And second, we have a polymodal distribution. So where you have 2 or more narrow bands of particle sizes, and each band will have its own maximum. Okay. So, and in between these two bands, there will be no particles. Okay. That is what the Pauli model. And next, Rodman distribution, which corresponds to the concentration of particle sizes over a rather broad size. So we will have the maximum amount of the size of the particle will lies within this band, and there will be no particles having sizes outside the range. So there will be no particle size which will lies outside the range, which is the broad band. And finally, we have an irregular distribution which presents a continuous and finite what we call it as variation of particle sizes within a relatively broad range. So this is what we were discussing in the last. I think I just ended up the last week class with this concept. Okay, so when you just want to review all these things, I just have taken a few minutes. So let us continue with the things, right? So in today's class, let us continue with the characterization of metal powders. So in that respect, we're going to start with the concept of interparticle friction and flow characteristics. See, whenever we produce a powder for making the powder metallurgy parts, okay, so the powders which will going to be formed, definitely it will going to be flow, means it will be once formed, it will be different techniques. So definitely the powder particles will have the interparticle friction. Interparticle friction is always will be having within the powder itself, and it will affect the flow of the powder during the production and even during the other processing techniques of the powder metallurgy. So how these interparticle friction and flow characteristics of the particles will going to affect in our powder metallurgy process, that is what we will going to discuss. The friction between particles affects the ability of the powder to flow readily and pack tight. So we are talking about the interparticle friction. Interparticle in the sense the friction between the powder itself, the powder particle itself. So this friction between the powder particles will definitely affect the ability of the powder to flow readily and pack tightly. So when you want to produce a parts for in powder metallurgy technique, so the compaction and sintering are the two different processes that will go to be takes place. So in such cases, we may find that the particles may not flow readily and they may not pack tightly. So therefore, the common test of interparticle friction is the angle of repose, which is the angle formed by the pile of powders as they are poured from the narrow funnel. So in the sense, so we can see this diagram over here. Okay, so this is the funnel. Okay, so the narrow funnel. So when you pour a powder through this funnel, okay, so you will going to get a pile of powder. Okay, so this is the angle of repose. I think you might have go back to your civil engineering where you have studied your the concept of friction. So the angle of repose will be there here. This is one. Okay, so you can see here. This is the pile of powders. So smaller particle sizes generally have greater friction and steeper angles. The particle size is very small, then the angle, that is friction between the two particles, will be more, and they will going to form the more steeper angle. And if the spherical shapes are there, there will be lowest interparticle friction. As shape deviates from spherical, friction between the particle tends to increase. So therefore, the most preferred size of a powder is sphere or a spherical. So therefore, if the shape deviates from the spherical, so the friction between the interparticles will going to increase. So therefore, the more prominence will be given for the shape of the powders, and we have to make the powder be in the spherical shape so that we can reduce the interparticle friction and hence we can improve the flow characteristics. So this is what the interparticle friction and flow characteristics. Okay. Next comes the compression ability. This is another important characteristic that needs to be understood with respect to the metal powders. Compressibility is a measure to which a powder will compress or densify upon application of external pressure. So compressibility, you know, so once you just apply a pressure, so how easily the powders will get densified. Okay, so the ability that it is a measure to which the powder will compress, or how fast it will compress, or how densify on the application of the external pressure. It basically, the compressibility is reported as a density in gram per centimeter cube, rounded to the nearest 0.01 gram per centimeter cube at a specified compaction pressure, or as the pressure needed to reach the specified density. Typically, a cylinder or a rectangular test piece is made by pressing powder in a tank with the pressure applied simultaneously from top and bottom. Generally, in the case of the powder metallurgy, once the powders are formed, once the powders of different materials you're going to get, so the next thing is you need to press it. Press it in the sense you press it by what we generally use the word called compaction. So compaction is the process of applying the pressure externally so that the powders will be gets compressed to form and they will bind and they will go to form the final. So here, generally, we in the powder metallurgy we use the cylinder or rectangular type of test pieces, and we're going to press it in the case in the tank with the pressure applied simultaneously both from top and bottom. So we're going to apply the pressure from both top and the bottom. Compressibility of powder is influenced by factors like inherent hardness of the concerned metal or alloy, particle shape, internal porosity, particle size distribution, presence of non-metallics, addition of alloying elements or solid. See this compressibility. So once you start compressing the powder particles, so there is a possibility that the compressibility will get affected by gets affected by the factors or influenced by the factors like inherent hardness of the concerned metal or alloy. So the type of metal powder you have made, the powders, the metals, they will have its own hardness that is inherent. Particle itself will be, metal itself is having a certain hardness, and of course it is a metal or alloy, whatever it might be, and the shape of the particle and the internal porosity, that is also very important. So what is the percentage of porosity is required, that is also important, and the distribution of the particle size, what type of distribution, whether it is a poly model or mono model, or whether it is a background, like that, different distribution or irregular distribution, and the presence of non-metallics and addition of alloying elements or solid. So these are all the factors which will going to influence the compressibility of the powder. Compressibility alternately is defined in terms of densification parameter, which is equal to densification parameter, which is equal to. So we have got the mathematical expression for a densification parameter. Generally, the compressibility will be represented or it is being expressed in terms of a parameter called densification parameter. So here, the densification parameter is taken as green density minus apparent density divided by theoretical density minus apparent density. So this is the densification parameter. Compressibility in general increases with increasing apparent density. A rather large amount of densification offers relatively low compaction pressure. In the sense, if the densification parameter is more, so you need a very less compaction pressure. A large amount of densification occurs at a relatively low compaction pressure. If the densification parameter is more, in the sense, if the powder particles whose densification parameter is more, then when you start pressing the powder, so the amount of external pressure required will be relatively small. So therefore, what we prefer in the metal powders is it needs to have larger values of densification parameter so that during the compaction process, you can apply a relatively smaller pressure. Yeah, next comes the powder structure or the particle shape. So we are talking about the size we have discussed, the different how we have discussed, the distribution of the sizes, particle sizes, and now the structure, the particle shape. So it can have different shapes also. So what are those shapes and how we can get these uh, different shapes? We're going to discuss it. There are various shapes of metal powders, such as one is a spherical, a carbonyl iron, that is the best example, condensed size, lead, atomization, precipitation from aqueous solution by gases. So that is the best method for obtaining the spherical shape of the powders. Rounded or droplets, atomized copper, zinc, aluminum, tin, chemical composition. Angular, mechanically disintegrated cast iron, stainless steel obtained by intergranular corrosion. This is the best process. So acicular, basically a chemical decomposition. So these are all the different powder structures what we are having. So these structures have been obtained with the different methods and the different metals also we are using here. So with the different examples, they have given atomized copper or carbonyl iron or whatever it might be. So cast iron or stainless steel. So different shape of the metal powders can be obtained by different processes also. We have some more things. So dendritic type of shape, electrolytic silver or iron powder, flakes, wall milled copper, aluminum, and stamped metals, porous reduction of oxides, irregular atomization, reduction, chemical composition. These are all the different types of structures or shape of the powders that we are going to get it from different metal powder techniques. Okay. So, so what type of final product you are manufacturing? So depending upon the requirements of the final product, depending upon the percentage of porosity what required in the final product. So we can decide which is the best method for us. So which method will going to produce the shape and the size of the particles that is more suited for obtaining the final product. So this is how we will going to decide. So different methods will going to give different particle structure or particle shape. So you have to decide which shape is required for us and which is the best suited for best suited particle shape or powder structure for our final. So this is how we can get the different shapes from different processes. And finally, we have fragmented. Particle shape has pronounced effect on the packing of powder and has influence on its compacting and sintering properties and the mechanical strength of the sintered product. Thus, irregularly shaped particles have reduced apparent density and flow rate, good pressing and sintering properties, while spherical particles have a maximum apparent density and flow rate, but reduced pressing properties and good sintering characteristics. The shape of the particle will have a more effect on the packing of powder. Packing of powder in the sense which going to take place during compaction and sintering. So this particle shape will have an influence on its compacting and sintering properties and also the mechanical strength of the sintered product. So therefore, the irregularly shaped particles have reduced apparent density and flow rate. So the particle shape is of irregular shape, then its apparent density will be reduced and also its flow rate will be reduced. But it will have a very good pressing and sintering property. Very good pressing and sintering properties. While the particle shape is of a spherical type, it will have a maximum apparent density and flow rate, but its reduced properties, pressing properties and sintering properties. The pressing properties will be reduced, but its good sintering characteristics. So depending upon what type of particles we can have, So this is a diagram what it is showing with different shape what I was discussing in the previous slides. So here, so different shapes here: spherical, angulate, rounded, cubic, acicular, irregular, flake-like structures, agglomerate, dendritic. Okay, flake-like, rounded, angular, irregular, like that. Different shapes you can see here. Uh, the particle shapes what it is being displaying over here. Okay, this is what we call it as an irregular type of powder particle shape. This is a rounded irregular, rounded irregular. Look at that, rounded irregular, and this is a flake-like powder particles, and this is sphere. Sphere. So this is what the different shape or the particle structures what we are showing here. So everything it is a polygon shape, flake-like structure, irregular, acicular, cubic, rounded, angular, spherical. This is spongy or the porous, spongy or porous, cylindrical. Like that, different shape of the particles we can see over here. Yeah. So once you understand, so the shape, the compressibility, interparticle friction, and flow rate, these are all what we generally discuss under the characterization technique. Next comes how we can control the microstructure in power. The importance of microstructures. So before we go for this, so what is the importance of microstructures? Because how we can control. So controlling the microstructure is a different case. But what is the importance of microstructure study? So first we should understand. I think this kind of microstructure study you might have done in your metal testing laboratory in your course semester, so where you know how to prepare a specimen for examining the different materials and alloys for its microstructure study. So here also we will same thing. Just we will have an extended discussion with the microstructure of importance. Okay. Microstructures determines the mechanical, physical, and chemical properties of it. See, when we just know what is the microstructure of that particular metal or alloy, whatever it might be, so that from the microstructure we can determine its mechanical, physical, and chemical properties. For example, the strength and hardness of the materials are determined by the number of phases and their grain sizes. The electrical and magnetic properties and also the chemical behavior are determined by the grain size and the defects present in the materials. This is a simple example they are giving. So how do we determine the material is more hard, and more strength? So if the number of phases and their grain size, based upon what number of phases it is in existing, and what will be the size of the grain. And the electrical, magnetic, and also the chemical behavior, especially the corrosion, is determined by the grain size and the defects present in the material. So maybe defects may be in the form of vacancies or dislocations or grain boundaries, whatever it may be. So the chemical behavior, electrical and magnetic properties, which can be determined by the size of the grain and what type of defects present in the microstructure or in the material. We are going to describe the different metal, electrical and magnetic, as well as chemical behavior of the particle. A complete description of microstructures involving describing the size, shape, and distribution of the grains and second phase particles and their composition, and also the defect structures, although these are often omitted. When you want to have a complete description of microstructure, we need to describe the size, shape, and the distribution of grains, and the second phase particles and their composition, and also the defect structure although these are often omitted. The defect structure generally we don't take, but when you say a microstructure, the complete description of microstructure, we just describe the size, shape, and distribution of grains and this. The microstructures of metal or alloy is not unique. They can be modified by different methods. A microstructure, it is not unique of any alloy or a metal. So you can import or you can change or you can modify the microstructure by different methods or different processes by allowing additions when new phase may appear, deformation processing when the grains may be elongated in the direction of working, phase transformations when a completely new microstructure may develop. Two common examples are the transformation of austenite to martensite when quenching a steel, or a perlite when steel is slowly cooled and heated. In the sense, how you can import different properties. So generally, we go for alloying or maybe a deformation process or phase transformations. So by using any of these methods, you can modify the microstructure of a body. So when you add a new element or when you alloy it, new phase may start, when new phase may appear in the microstructure. Or when you deform a material, the grains may get elongated in the direction of working. It is just like a malleability or ductility, how you just deform the material with different forms. And of course, when the heat treatment, when you heat treat it, the phase transformations may take place, where completely a new microstructure may develop. So that's what simple example they are given: the transformation of austenite to martensite when quenching a steel. When you quench a steel, so the transformation from austenite to martensite, or from austenite to perlite when steel is slowly cooled and annealed. See, there are different processes. So quenching is a rapid way of cooling. Okay. So when you cool an austenite or when you quench a steel, so the austenite structure gets transformed into the martensite structure. Or same steel, it is being cooled slowly and annealed. The austenite is just converted into perlite. So this is what the simple examples they are giving. So how you can modify the structures by a phase transformation. So these are the different methods by which you can transform the methods, right? Next comes microstructures of powders by different techniques. So we have one table, overview of powder characterization techniques commonly used in additive manufacturing. The next slide I will show the table. So this is the microstructures of powders by different techniques and characterization techniques commonly used in additive manufacturing. Okay, I will show this table. So this table is a little bit very small, but I don't have any other option because this is the one table where you can understand each and everything. Each and everything you can understand over here. Yeah. See, this is the table which we are going to explain us for the different powder characterization techniques which commonly used in additive manufacturing. So we have a techniques, the materials, resolution, particle size range, advantages and disadvantages. Okay. So, so these are different particle morphology. They have given particle chemistry, particle microstructure. So different techniques they have with particle morphology. So we have sieve analysis or microscopy or laser diffraction. So type of particles, materials, we can use any kind of solids depending on the microscope. And the resolution, of course, they have given different resolution for different techniques. The particle morphology, is just the size. What kind of size of the particles you can get. Particle size is the particle morphology. So where you can get the particle morphology by sieve analysis or microscopy or laser diffraction. Okay. So the particle size range they have given in the fourth column. Fourth column you can see it is 20 micrometer to 125 nanometers. 20 micrometer to 125 nanometers particle size you can determine by sieve analysis. So in the case of microscopy can be determined by the system resolution depending upon what type of resolution the system is having. So the system resolution they have given here, and in using the laser diffraction you can have 0.04 to 8,000 micrometer. So this is the particle size range what you can determine from the laser diffraction. So the advantages of sieve analysis applicable to a broad size range, minimal sample preparation, low cost, whereas a microscopy allows qualitative and quantitative observation of particle shape, flexibility for particle shapes and shape analysis. And whereas the laser diffraction, short analysis time does not require a skilled labor, highly repeatable. And when it comes to the disadvantages of sieve analysis, so no insight into the particle shape, longer measurement time, prone to a blinding particles with large aspects. So like this, different advantages and disadvantages. You can just go through this in your free time. Okay. Then particle chemistry. So particle chemistry, in the sense, what is call it as the composition of the particle. So we have XPS, AES, EDS, Fourier transform IR spectroscopy, inductivity coupled plasma osmotic experiment. Like this, different techniques we are having here. So each technique will have its resolution, and it will have the particle size range and their advantages and disadvantages. And when it comes to the particle microstructure, so we have XRD, FIB, transmission electron microscopy, what we call it as a TEM, transmission electron microscopy, and we can have a thermal analysis. Okay, so here the resolution phase must have a concentration greater than or 5%. Here in the case of FIB, it is 1 micrometer. It is the resolution, it is in the type of atoms. Thermal analysis is 1 to 2 degrees centigrade. Yeah. So these are all some of the different powder characterization techniques what we are having. So please go through these things because it's very simple to understand. I think it's very process or technical information. Just only they have given the list of the techniques and their techniques and resolutions, their particle size and advantages and disadvantages. So you can go through this. The next comes particle shaping. Particle packing modification. So how the modifications can be done in particle packing. So generally, the packing factor, we generally describe it as a bulk density to the true density. Typical values for loose powders range from 0.5 and 0.7. Powders of various sizes give higher packing factor. Packing can be increased by vibrating the powders, causing them to settle more tightly. Pressure applied during compaction greatly increases packing of powders through rearrangements and the deformation of particles. So here, when the metal powders are produced, the sizes of the particles will be distributed in a different ways. The shape will be different. Okay. So the most important thing is the particles, they need to have its own ability to get compacted and get sintered so that we can obtain the final the product. So to get a final product, ultimately what we want is the packing factor. So how densely the particles or the powder particles gets packed in this. So therefore, this is what we call it as packing factor is bulk density, the fluid density. And generally, the typical values of loose powders for packing factor will range from 0.5 to 0.7. So powders of various sizes give higher packing factor. So different sizes will give different packing factor. Packing factor can be increased by vibrating powders, causing them to settle more tightly. Pressure applied during compaction greatly increases the packing of powders through rearrangements to the deformation of the particles. So this is how it has been the void. If the void is more, so smaller and more numerous voids, void filled by smaller particles, small void. So how we can minimize the voids. So if the voids are very small, then the packing factor will be. So I will stop at this point in today's class. So I will continue in the afternoon class. So if anybody is having any clarification, you can add. Okay. If anybody is having any clarification, you can talk to me. Anybody has got any clarification, any doubts, the following? So I have already loaded this course material in the Google Classroom. So please refer that. Still, if you have any clarification, you can talk to me. Okay, we will meet you in the afternoon class at 1:45. Okay, so we'll just continue with the same concept.
Okay, sir.
Okay, thank you.